All right, so we're gonna continue where we left. So in this session, remember we have discussed a lot of things, right? So far, we spoke about the concentration, we spoke about the empirical formula, the number of moles. We did a lot. So now we're gonna continue with this concept, which now says amount of substance. Mole, we know amount of substance, it refers to mole, where we actually going to discuss the molar volume of gases, concentration of solutions. So by the end of this, we're gonna perform the complex calculations involving what we have already started with. Okay, so under this, sorry about that, it's not examples, it's a content. Now with the content that we have over here, we're going to talk about the molar volume, right? So when you talk about the molar volume, what are we actually talking about? Again, it's very important to know how to define a molar volume. So here, right here, I gave you the definition. The molar volume of gas is defined as follows. We say the volume occupied by 1 mole of any gas at STP. So in that case, that means, let's say maybe we have a vessel. Now, this is a closed vessel, maybe, for an example, and then we have the gaseous molecules inside of this vessel, right? These are the gaseous molecules. Let's say the temperature at which these gaseous molecules are is 0 degrees Celsius. And the pressure of these gaseous molecules, it is 1 atmosphere. Now, when these gaseous molecules experiencing a temperature of 0 degrees and a pressure of 1 atm, we say the volume occupied by these gaseous molecules, it has what we call the molar volume. That's why here we say the molar volume of gas is defined as the volume occupied by 1 mole of any gas at STP. So 1 mole of this gas at the standard temperature and this standard pressure, we say that this molecule, they occupy a volume of molar volume. We say it has a molar volume. Okay. So the value of this volume at STP, the value of this volume is going to be 22.4 cubic decimeter per mole. Here we left, okay, it's going to be molar volume. It's the same as 22.4 cubic decimeter per mole. These are the units for this numerical value of molar volume. So STP, ne? S means standard, T means temperature, and P means pressure. So that means STP refers to the condition known as standard temperature and pressure. Now, a standard temperature is when we have 0 degrees Celsius. Or if you don't want to use your temperature in degrees Celsius, maybe we want to use our temperature in units called Kelvin. So we're going to say the temperature is 273.15 Kelvin. This is a standard temperature in these units called Kelvin. And this is meaning 0 degrees is the same as 270.15 Kelvin. This is the standard temperature. But the standard pressure is when we have 1 atmosphere, 1 atm. It means the units for pressure, we also use the atm, which is the atmosphere. Or we can use the kilopascals. Or if you don't want to use the kilopascals, you can use your pascals. Okay, so when they talk about this pressure and this temperature, just know that they are talking about the standard temperature and pressure. I'm saying this because maybe at some point they will ask you to calculate the number of moles at the temperature of 0 degrees Celsius and 1 atmosphere. Sometimes they're not gonna say calculate the number of moles at STP. They can say calculate the number of moles at 0 degrees Celsius and 1 atm. So when they say at 0 degrees Celsius and 1 atm, in your head, you're supposed to know that they are talking about the standard temperature and pressure. So it is not always the case where they're going to say, calculate the number of moles at STP. They can say, calculate the number of moles at 0 degrees, at the temperature of 0 degrees and the pressure of 1 atm. So that actually refers to the to standard temperature and pressure. Okay. So calculation on molar volume, we're going to use this equation over here. It's the same as this one. Let me take the big one. We're going to use this equation to calculate the number of moles. So meaning this is the volume of that gas, but this is the molar volume constant. So we use the molar volume constant, which is denoted by 22,4 cubic decimeter per mole. Okay, so we know that N is the number of moles, the units mole. V is the volume of gas, the units cubic decimeter. And then Vm is the molar volume of gas, the units is going to be cubic decimeter per mole. So now let us quickly jump to the example. Now here they say calculate the number of moles in 120 cubic decimeter of neon at STP. You see, sometimes they're not going to say at STP. Sometimes instead of them saying STP, they're going to say at 0 degrees Celsius and 1 atm. You're supposed to know what are they actually talking about. Okay, so right, fine. Let's perform our calculations then. All right. So now, start with 6a. Now, question number 6a, we want to calculate the number of moles, right? We want to calculate the number of moles of neon at standard temperature and pressure. Okay, so we are given the volume. The volume is 120. V, it's 120 cubic decimeters. And then at STP, we know that we have the molar volume, which is denoted by 22, because neon is a gas, okay? 22,4 cubic decimeter per mole. Now, let's determine the number of moles. We know the equation that we use is going to be N is equals to volume divided by the molar volume. There are many equations that we can use to calculate. By now. We know we have the equation N is equals to, we have the equation C is equals to N over V. We have the equation N is equals to mass over molar mass. We have the equation, which is the one that we have just learned right now, which is V divided by Vm. If they say to you, calculate the number of moles, you're supposed to know what is given and what are you calculating. So we cannot use this equation. We are not talking about the concentration. Yes, it's true, we are given the volume. You cannot use the equation. You are not even given the mass. It's totally out. But we can use this one because they say it at STP. So always, this is the hint. When they say STP, think of this formula here at least. Okay. So our volume in this case, it's given to be 120 cubic decimeters. The units are correct. It's decimeters. We don't have to convert. And then the molar volume is going to be 22,4 cubic decimeters per mole. Therefore, when we punch everything on our calculator, we're going to say 120 divided by 22,4. And then on my calculator to 2 decimal places, I get 5,36 mole. So these are the number of moles calculated. Simple as that. And therefore, we jump to 6b. Now 6b, we still have to calculate the number of moles at STP and the molar volume. Again, at STP, we know it's going to be 22,4 cubic decimeter per mole. Now, the volume of what? We want to calculate the number of moles of what? Of helium, right? And we are given the volume of helium to be 5.6 cubic decimeters. So to calculate the number of moles, we're going to use the formula N is equals to volume divided by the molar volume. And in the volume there, we have 5.6 divided by molar volume, which is 23.4. And when we punch everything on our calculator, we're going to say 5.6 divided by 22.4, we get 0.25 moles. So this is the number of moles for helium at STP. And then we are actually done. All good. Do you understand how I went about? So now, let's continue with the content once more again. The last content. This is the last content. So now we're going to talk about what we call the theoretical yield and calculations. Now, when we talk about the theoretical yield and calculations, what are we actually referring to? What are we talking about? Now, let me tell you something. Let me tell you something. This, I'm not good at drawing. I'm not really good at drawing. So what do you see over here? Let's assume that it is a company, right? It's an industry. In this industry, what's happening is they produce gold. For example, they produce gold, right? So what's happening is the miners, people who work at the mines, they're going to extract the raw material from the earth's surface and they take it into a company, right? And then this company, what it does is it is going to refine that gold, right? They want to extract the gold from the earth's surface. But what you need to understand is that a gold, it doesn't come as it is. It doesn't come as pure gold from the earth's surface. I get these guys, they go to the mines, they dig the holes, and then they get all of these things from the mine. But what you need to understand is that this, it doesn't come as a pure gold. So meaning they're gonna get material from the earth's surface that has gold in it. There is a gold there. There are other metals like iron. There are other metals, maybe, let's see. Sorry about that. Up, what happened there? The other metals here. There is another one here. There is another one there. There is another one there. And there is a gold again. There is this, there is that, there is that. Meaning this gold, it is not pure gold. So we're going to take this sample and we call this sample impurity. So this impurity, it is impure because it composed of many different elements. It is not only gold. Some are not even useful. Some are useful minerals. Some, it's just a lot going on because it is coming from the earth's surface. So what this company will do is they will refine this and then they will extract gold. At the end of the day, they want to extract gold from these impurities. So because it's a company, this is what we call the actual yield, right? So meaning this company will take the impurity and process that impurity, clean or purify that impurity and get gold. When this company get gold, we say this is a yield. When we say something, it is yield. It's when you you produce. Okay, when you yield something, you're producing something. Okay, yield and produce kind of the same things, like synonym. So this company, they're gonna yield gold with a certain percentage, or they're gonna produce gold with a certain percentage. So that percentage that this company will produce, it is the actual one, because it is the one that they are doing at that point in time. Okay, it is called the actual yield. It's called the actual yield. The gold that the company will produce, it is the actual yield because this company actually produces this percentage of gold. 20%. Here, it looks like 100% of gold. But at the end of the day, they're gonna get only 20% from these impurities. They're only gonna get 20% of gold. That's an actual yield. Okay? And therefore, the theoretical yield, it is the yield that they wish they could have produced of gold. It is the yield that they wish they could have produced. Meaning theoretical yield is what they're gonna perform based on the calculations. Meaning they're gonna perform theoretical yield using the stoichiometric calculations based on what they've got, which is this impurity. They're gonna perform their calculations, and maybe they wish to produce 50% of gold, but actually they produce 20% of gold. But theoretically, on their books, they wish that they could have produced 50% of gold. You understand? So the difference between the actual yield and the theoretical yield, let's have a look at this definition. The actual yield is the amount of product obtained from the lab data. So this company, let's take it as it's a lab. And actually, this is what they produce. It's an actual yield. But the theoretical yield is the amount of product obtained from the stoichiometry. Remember, stoichiometry is the calculations. Number of moles, the very same thing that we have been busy doing. That's the stoichiometric calculations. We've been performing stoichiometry. You understand? So stoichiometry is when we calculate the number of moles, the concentrations. That's stoichiometry as it is. That's why here on this mini information that I gave, I said that the theoretical yield is the maximum yield. Yes, it is the maximum yield because they wish to produce that. And it's impossible. It's impossible for them to produce that. That's why different companies, we have chemical engineers. That's why we have the chemists, because that's what they work with. They work on a profit of a company. They want to know what can these chemical engineers or what these chemists can do to improve the product of the company. You understand? So if maybe you want to be this kind of person working with these things, you have to be a chemical analyst, or maybe you have to be your engineering, or you have to be whatever along those lines, so that you can work for a certain company, and then you do your calculations where you see how to maximize the yield of the product, how to form more product. So you have to perform all of these calculations. It's a task that will be provided to you as a chemical engineer or a chemical analyst. So the theoretical yield is the maximum yield, okay? That can be obtained when all the reactants react completely. This is calculated from the balanced chemical equation. That's the theoretical yield. In practice, the theoretical yield may not always be obtained because there may be impurities present in the reactants. Like I said, there are impurities present. Because of those impurities, we're going to have to eliminate a lot of things from the impurities. Because we thought it's a pure gold, it's not. We have to clean it. When we clean it, we're going to see that it is not pure gold only. Because we thought it's 100% gold, but now it's 20% gold. Because we had to remove impurities. Okay, so that's how it actually works. So do we understand what is it all about when you talk about the actual yield, the theoretical yield?
Yes, I understand.
Awesome. Now, and then we have what we call the percentage yield, which is the percent yield. The percentage yield, it refers to this company produce what percent yield of this gold. We use that against the actual yield and the theoretical yield. We want to check between, if we have this theoretical yield, we produce how, it's like we want to check the loss, because we're using the theoretical yield and actual yield. We want to check the loss. So now let me show you. I like I said, this is 20%, right? Actual yield. So when we say 20%, divide by 50%, multiply by 100, we're gonna get 20 divide by 50. It's gonna be 2/5 multiply by 100. We get 40. We're gonna get 40%. So that means we're gonna get 40% of 100 or 50%. Theoretical yield, it's 50%. We didn't get that 50%. How much did you get of the theoretical yield? We got 40% because we used the actual one. That's what I'm saying to you. Theoretical yield is a very maximum yield that it is impossible to obtain. So it's either we obtain that theoretical yield if it's possible, or we obtain less of the theoretical yield, which is 40%. Now we call that a percentage yield. Right. So I want us to perform the calculations. Let's have a look at the calculations based on what we have just learned. So now here they say to us, sodium hydroxide solution reacts with okay, here it's not, let me see something, calculate the mesos. Yeah, this is not the percent, this is not it, but yeah, I think, okay, we'll do those questions from the exam papers with time. Okay, it's fine. Let's see here what's happening. The sodium hydroxide solution, sodium hydroxide solution reacts with sulfuric acid to produce sodium sulfate, and water according to the following balanced reaction equation. So apparently we can see that, okay, it's fine. Let me complete reading everything. And they say to us, if 20 grams of sodium hydroxide, this is our sodium hydroxide, if 20 grams of sodium hydroxide reacts completely with sulfuric acid, which is this, calculate the mass of the sodium sulfate produced on the product side. So we want to calculate the mass of this guy over here. We want to know the mass of this guy over here. That's the question. So look, we have 2 moles of sodium hydroxide reacting with sulfuric acid to form sodium sulfate and water. We are given the mass of sodium hydroxide to be 20 grams. We are looking for mass of sodium sulfate. Now, for a fact that they said sodium hydroxide reacts completely, that means sodium hydroxide, it is called the limiting reagent. So sodium hydroxide, for a fact that it's going to react completely, what does that mean? That means we can use that sodium hydroxide to calculate the number of moles of everything that we see on this equation. If I want to calculate the number of moles of H2SO4, I'm going to use sodium hydroxide. If I want to calculate the number of moles of sodium sulfate, I'm going to use sodium hydroxide. If I want to calculate the number of moles of water, I'm going to use sodium hydroxide. Why? Because sodium hydroxide reacts completely. So for a fact that it reacts completely, that means sodium hydroxide, it is called the limiting reagent. That is why. Right, fine. Remember what was the question? They wanted us to calculate the mass of sodium sulfate. So in order for me to calculate the mass of sodium sulfate, firstly, I'm going to need to calculate the number of moles. And when I get this number of moles, I will convert that number of moles into mass. So firstly, I need to do this. This is the first step. Actually, this is what I need so that I can calculate my mass. But remember, what did I say to you? I said I can use sodium hydroxide to calculate the number of moles of everything. So if I want to calculate the number of moles first for sodium sulfate, let me talk about the number of moles of sodium hydroxide so that I can use those number of moles to calculate this number of moles. And the another thing is make sure that your chemical reaction, it is always balanced. They told us that this reaction is balanced, so we can use it. But if you were to start your own equation, you had to model your own equation, then balance it after doing your equation. Sometimes they don't give you equation. You have to do it yourself. It depends on the question. So if you have to do it yourself, then make sure that that equation, you balance it. So this one is balanced. Right. So firstly, we're going to determine the number of moles of sodium hydroxide. That's what we're going to do. So to get the number of moles of sodium hydroxide, we're going to use the equation mass divided by the molar mass. Um, we're going to use the equation mass divided by the molar mass, right? Now, after using this equation, just want to do this thing is disturbing me here. Sorry about that. All right. Okay, so we're gonna do this, ne? So we are given the mass of sodium hydroxide to be 20 grams, ne? Now, what we're gonna do is we're gonna have to calculate the molar mass of sodium hydroxide. It's not a problem because we can use the periodic table to calculate the molar mass of sodium hydroxide. So to calculate the mass of sodium hydroxide, let me do it here. Okay, let me do it this side. Molar mass of sodium hydroxide. Remember our sodium hydroxide over there. Our sodium hydroxide over there, we're gonna have its sodium plus oxygen plus hydrogen. So sodium in this case, what is from the periodic table, we know that sodium is gonna be, okay, let me use this one. Sodium is gonna be 23. So for sodium there, we have 23. And for oxygen there, we have 16. For hydrogen, we have 1. And therefore, we're going to say 23 plus 16 plus 1, we get 40. So the molar mass will be 40 grams per mole. So we're going to substitute then to get the number of moles of sodium hydroxide. So mass there is 20 grams, and then the molar mass is going to be 40 grams per mole. And therefore, what will be the number of moles for sodium hydroxide? So we're going to say 20 divided by 40, we get half, which is 0.5. Then we get 0.5 moles, right? So the number of mole for sodium hydroxide will be 0.5 moles. Now, like I said, to determine the number of moles of sodium sulfate, we're going to use sodium hydroxide. We're going to use this number of moles of our sodium hydroxide. How? We're going to use the balanced chemical equation. That's why I say to you, the balanced chemical equation is important because it's going to help you to determine the number of moles. So according to the balanced chemical equation, according to a balanced chemical equation, what are we going to do or say? According to a balanced chemical equation, we're going to use the ratios, right? For sodium hydroxide, which is what we are using. We're going to say sodium hydroxide is to this side, we use sodium sulfate because that's what we are looking for. We're going to say sodium sulfate. And therefore, what is the number of moles of sodium hydroxide? We just calculated to be 0.5, right? So on this side, we're going to have 0.5 moles is to what is the number of moles of sodium sulfate? We do not know the number of moles of sodium sulfate. So that's what we are looking for basically, right? That's what, here's our question mark. That's what we are looking for. So we're going to say number of moles of sodium sulfate. And therefore, now we're going to use the stoichiometric coefficients after that. Here we have 1, and then there we have 2. So for sodium hydroxide, we have 2. And for sodium sulfate, we have 1. And then using this ratio, what we're going to do is we're going to cross multiply. This multiply by that, and 1 multiply by 1. And therefore, we're going to have 2 multiply by the number of moles of sodium sulfate. And then we're going to say 1 multiply by 0, 0.5. It will be 0, 0.5. And then we divide both sides by 2. Then we left with number of moles of sodium sulfate. And then we're going to say 0, 0.5 divided by 2 is going to be 0, 0.25. We get 0, 0.25 moles. Now we have the number of moles of sodium sulfate. But the question was calculate the mass. We know now we can convert this number of moles into mass. But how? Using the equation, number of moles is equals to mass over molar mass for sodium sulfate, right? For sodium sulfate, we're going to have to calculate the molar mass. The molar mass for sodium sulfate, it's going to be how many sodium do we have? We have 2. So we're going to say 2 multiplied by Na plus sulfur. How many oxygens do we have? We have 4. We're going to have 4 multiplied by O. So we're going to say 2 multiplied by Na is going to be 23 from the periodic table. And the sulfur is going to be, I think, 32. Sulfur, where is sulfur? Number 16, yes, is going to be 32. So sulfur is going to be 32. And for oxygen is going to be 16. And therefore, when we punch everything on our calculator, we're going to say 2 multiplied by 23 plus 32 plus 4 multiplied by 16. And then we get 142 grams per mole. Then we can calculate the mass. Let's cross multiply. We have mass multiplied by 1, it's mass. Therefore, number of moles multiplied by molar mass. Therefore, what is the number of moles for sodium sulfate? We saw that we got 0, 0.25 multiplied by the molar mass. Molar mass is going to be 142 grams per mole. Therefore, when we multiply these two guys over here, we're going to say 0, 0.25 multiply by 142. Then how much do we get? We get 35.5 grams. Therefore, this will be the final answer. Now we managed to do what? Now we managed to get the mass for sodium sulfate produced, which is this.